Starting a new chapter. Chapter 5 is about discrete probability distributions. We're going to take all of what we've learned in the first 4 chapters and put them together and start looking at probability distributions for data. To begin, let's remind ourselves the difference between discrete variables and continuous variables. Discrete variables are quantitative variables that can be counted, and continuous variables are quantitative variables that need to be measured. So the example that I used back in chapter 1, a discrete variable would be how many eggs a hen lays, because a hen can only lay whole number eggs. We have to count them. Even if we have a double yolk in that egg, it's still one egg. And for continuous variable, how much milk a cow produces. A cow doesn't have to produce whole gallons of milk. We have to measure it using a measuring cup. So we could say maybe the cow produces 3.24 quarts of milk that day. Walk through this warm-up and see if you can identify whether the following are discrete or continuous. When you resume, I'll have the answers for you. So for these examples, B is the one that is discrete. The number of people who play the state lottery each day. That is a count, how many people. So that's a discrete variable. There's a little question on whether or not the time it takes to have a medical physical exam is continuous or discrete. Usually we say that time is continuous. We can have fractions of a second. There could be some argue for discrete there as far as counting the minutes. But again, we can have partial minutes. So I think it's continuous. The next thing I want to do before we define our vocabulary words for this section is to also recall our probability properties that we got in chapter 4. There are 2 of them. The first one, any probability that we have must be between 0 and 1. We cannot have negative probabilities and we cannot have probabilities bigger than 1. If we're talking percents, they can't be bigger than 100%. It doesn't make sense. 1 means it's absolutely certain that it's going to happen. 0 means there's absolute certainty that it won't happen. The probability is the continuum between those 2 numbers, including 0 and 1. And the second probability property that we talked about is that if we add up all the probabilities in a sample space, we would get 1. Keeping these things in mind, let's remind ourselves of a random variable. A random variable is a variable whose values are determined by chance. We're also going to look at it as a numerical outcome of a probability experiment. So if we're rolling a die, the random variable would be one of the numbers between 1 and 6, the numbers that we could land on if we rolled the die. Here we're always going to be considering quantitative variables, hence our exercise on discrete versus continuous. We're looking at quantitative variables, so our random variable will be quantitative. A discrete probability distribution is essentially a table. It's usually expressed as a table that consists of all of the values that a random variable can assume and the corresponding probabilities of each of the values. So let's look at some requirements for a probability distribution. The first big one, we have a numerical random variable x, and its values are associated with some corresponding probabilities. So we have x, and we have p of x. Also, the sum of all the probabilities equal 1, and each probability is between 0 and 1 inclusive. So we have the same properties for probabilities in a sample space that we have for our discrete probability distribution. A probability distribution can be related to a frequency distribution, but instead of listing out frequencies, we list out probabilities. Also, a relative frequency distribution is essentially a precursor for a probability distribution. If we make the relative frequency percentages into decimals, we have a probability distribution. So we've already created a discrete probability distribution if we've had discrete data that we put into a frequency distribution and then created a relative frequency distribution from it. They are very similar. In some cases, though, a discrete probability distribution, instead of being a table with columns, sometimes it's written as a table in rows. And you'll see me do that in the first example. Let's talk about a procedure for constructing a probability distribution. First, we'll make a frequency distribution for outcomes of the variable. And this frequency distribution is not a grouped frequency distribution, it's a categorical frequency distribution, one where we only have one value representing each class. And then we find the probability of each outcome by dividing each frequency by the total number of data values. That's exactly how we find relative frequency. We usually just change it to a percentage. We're going to keep the probabilities as decimals in our probability distribution here. And then if a graph is required, we'll place our outcomes on the x-axis and the probabilities on the y-axis and draw vertical bars. Let's try one together. We're going to construct a probability distribution for the following data for 10 students. The data represents the number of people living in their household. So I'm going to utilize the space on the left. We'll put x, our random variable, up top, and we'll put our frequency on the bottom. So usually we were creating tables vertically like this, and we would write 2, 3, 4, 5, and 6. Those are the values represented in our data. And we can still do that. We absolutely can still do this kind of table. I'm just showing you a different way to present it. So the values that x can assume, 2, 3, 4, 5, and 6. We don't have any 1s here. We don't have any 7s or anything higher. So we're just going to list out the different values of x. And then we count how many times each one shows up. 2 shows up twice. 3 shows up once. 4 shows up 3 times. 5 shows up twice. And 6 shows up twice. So creating a frequency, now we can use that to create our discrete probability distribution. We'll keep the x and the labels 2, 3, 4, 5, and 6. But instead of frequency, now we're talking probability. And this can either be p of x or just p. Either one is fine. Using the frequency values, I'll take the frequency divided by the total number of data values, 10, and I get my discrete probability distribution. We usually like these to be reduced fractions or decimals, so we're going to make that change. I'm just reducing my fractions. The 2/10 are really 1/5. And then I'm going to do one more change, and I know I'm going off of the page here. I apologize. 2, 3, 4, 5, and 6 again. And this time we'll write them as decimals. So instead of a fraction, we'll write them as decimal numbers. And this first one or this second one, these are my probability distributions. Either one, expressed as a fraction or a decimal, doesn't matter. Now, let's represent graphically the probability distribution for the sample space for the number of people living in the student's household. So we're going to take this probability distribution and create essentially a histogram, but it's a probability distribution graph. So along our x-axis will be our outcomes, 2, 3, 4, 5, and 6. And then our probabilities, 0.1, 0.2, 0.3, 0.4. And then our bars are the heights of the probabilities for each one. So 2 is 0.2, 3 is 0.1, 4 is 0.3, 5 is 0.2, and 6 is 0.2. It does not matter if the bars touch or not. It's not a big deal. Seems to be a little bit neater if they touch. but for this, the bars can or cannot touch. It doesn't matter. And there we have our graphical representation of our discrete probability distribution.